Okay, so today we are going to talk about implicit differentiation. So our objective is that students will be able to use implicit differentiation to find the derivative of a function. So this is our last lesson for this unit, so for our differentiation unit. So let's go ahead and get started. So a little information we need to know. So implicit differentiation. So far, most functions have been expressed explicitly. For example, in y equals 1 over x, y is defined explicitly. In x times y equals 1, y is defined implicitly, or it is implied. So we can use implicit differentiation to find derivatives of functions where y is defined implicitly. When you differentiate terms with x, it's business as usual. So you do exactly what you do when you differentiate with terms of x. What changes is when we actually differentiate in terms of y. So when we differentiate in terms of y, we have to apply the chain rule. And we'll see how that looks right now. Okay, so when we differentiate with respect to x, here's some example. So this just means we're differentiating with respect to x right here. And so we want to find that derivative. So since the x and the x's are the same here, we are going to just differentiate as normal, right? So we can differentiate this, and this is just going to be 3x squared. That's that. It doesn't matter about using the chain rule because we only have terms of x in this function. But over in part B, we have this. It says we're differentiating with in terms of x, but our function is in terms of y. So we have to apply the chain rule. So the first thing you do is you take the derivative of y cubed like it was x cubed. And all you do is just differentiate that. So you get 3y squared, but you have to apply the chain rule. And basically what you're applying to it is the fact that you have to differentiate y with respect to x, and that's that dy over dx. So you have to add that in there every time you see a y. So anytime you differentiate a function with a y term, you have to add that to it, multiply it by that term. Okay, so let's try part C. So we want to differentiate with respect to x, but we have this y here. So it's kind of business as usual. So if we're differentiating x, we get 1 plus 3y, so we would get 3, but we would have to multiply by that dy dx to tell us that we differentiated y in terms of x there. Okay, so now part D, we have the same thing going on here, right? So, but we have a product rule. So we can separate this out as x times d dx of x squared plus y squared times the derivative of x, right? Because that's what our our product rule says. So then we have x times, well, the derivative with respect to x of y squared is 2y dy dx. And then we're going to keep the y squared and take the derivative of x, which is just 1. So we get 2xy dy dx plus y squared. And that's the derivative of this function right here. Ooh, that's wobbly. Okay, so here's some guidelines for implicit differentiation. So you want to differentiate both sides of the equation with respect to x. Then you're going to collect all the terms dy dx on the left-hand side of the equation. Then you're going to factor out dy dx out onto the left side. so it's by itself, and then you're solving for dy dx, right? So you want your end product should be dy dx equals the rest of the function, or whatever the rest of the function may be. So go ahead and make sure you write these down so you know the guidelines for implicit differentiation. Alrighty. Okay, let's work on example 2 here. So we want to find dy dx given that we have, oh, this is kind of hard to see here. We have y cubed plus y squared minus 5y minus x squared equals -4. So we want to differentiate both sides with respect to x. So we can differentiate each part since we're just adding and subtracting. So we have 3y squared times dy dx plus 2y dy dx minus 5 dy dx minus 2x equals 0, because the derivative of a constant is just 0. Okay, so now we want to collect all the dy dx terms on one side of the equation and move all the other terms to the other side. So all of these here have dy dx in them, so I'm going to leave them here. And I'm going to add 2x to both sides. And then I'm going to get 3y squared dy dx plus 2y dy dx minus 5 dy dx equals 2x. Okay, now since all of these terms have a dy dx, we can factor that out. So dy dx times 3y squared plus 2y minus 5 is equal to 2x. And then now you want to solve for dy dx, so we got to divide all of this to both sides, TBS, so 3y squared minus 2y minus 5. So dy dx is equal to 2x all over 3y squared minus 2y minus 5. Okay, so that means that this is our differentiation of y. So we differentiated y with respect to x, and this is the function we got out. Oh, that x looks weird. Okay. And so this is our derivative. Okay, so let's find dy dx given that sine y is equal to x. So we want to differentiate both sides again with respect to x. So we need to differentiate sine y and then multiply by the dy dx. So the derivative of sine is cosine y dy dx. And then we can just differentiate x as normal, right? So that's just 1. So then again, we're solving for the dy dx here. So we can divide both sides by cosine y. And then we get dy dx is equal to 1 over cosine y. Okay, so you're just taking the derivative of both sides as normal. But if you take the derivative of something with a y, you just multiply dy dx by it, and that's how you use implicit differentiation. Okay, and then in the end you want to end up solving for dy dx. Okay, example number 4 here. So we want to find dy dx given that y is equal to cosine xy. Okay, so now we have a chain rule on, and a product rule on our function. So we want to differentiate both sides with respect to x. So when you just differentiate y, right, you get dy dx. Ooh, x. That's an x, guys. Okay. And then you want to differentiate cosine xy. So the derivative of cosine, right, the outer function, is negative sine xy times the derivative of the inside, which is x times the derivative, dx, dy dx plus y times the derivative of x, which is 1. Product rule, chain rule. Okay, so then now we have negative sine xy x dy dx plus, nope. Okay, I'm distributing, sorry. So it's going to be negative sine xy plus, oh no, oh, I forgot what I was doing, times y. Okay, so remember we want to get all our dx, dy's on one side, so I'm going to rewrite this. So we need to add sine xy x dy dx to both sides. Gonna get a little sloppy. Okay, so when we do that, now we have dy over dx plus, I'm gonna do x sine xy dy dx. Just move that x over, and then that's negative y sine xy. So now here we have dy dx and dy dx, so we can factor that out. So now we have dy dx times 1 plus, forgot the x sine xy equals negative y sine xy. Should give myself more room. So now we can divide by this 1 plus x sine xy, 1 plus x sine of xy. So dy dx is equal to negative y sine xy all over 1 plus x sine xy. Whew. All right. Sorry, I ended up changing colors there. So that's our final answer. That's our derivative of y with respect to x, and it was a doozy, but we did it. Okay, number 5. Example number 5. Let me change my color. Okay, so find the slope of the tangent line to x squared plus 4y squared equals 4 at the point square root 2 negative 1 over square root 2. Okay, so first we want to differentiate with respect to x because we want to find the slope of a tangent line, so we need to find it. So we're going to do, okay, so when we differentiate x, we just get 2x. When we differentiate with y, we get 8y dy dx equals constant, so it's 0. So let's subtract 2x, subtract 2x. Now we want to solve for dy dx all the time, okay? Divide by 8y, divide by 8y. So dy dx is equal to negative x over 4y. Okay, so there's our tangent line. So let's find the slope. So we got to plug in the two values here. So dy dx is equal to, well, x is the square root of 2, so negative square root of 2 times, divided by 4 times negative 1 over square root 2. So that's negative square root 2 over, I don't know what just happened. Negative 4 over square root 2, which is negative 2 square root 2 times square root 2 negative over 4, which is 2 over 4, which is 1/2. So the slope of the tangent line here, so this is the slope of the tangent line at square root 2, comma, negative 1 over square root 2. Okay? Okay, so that's the end of what this video is going to cover. Tomorrow in class, we will do example 6 and 7. They're a little bit more lengthier implicit differentiation problems, so I want to show those two examples in class, and then we will start on the in-class work after we do that and after I answer any questions that you guys might have. Okay? See you tomorrow.